Okay, good afternoon, everybody. I'm going to talk a bit about algebraic data types, what they are good for, how can we use them in Scala, and at the end, maybe some a bit surprising connection between algebraic data types and mathematics. My name is Jiří Jakeš. I work for a small startup company in Taipei. The company's name is Bubble Eye. We work in advertising industry. Our backend is completely written in Scala with a little bit of akka. And of course, we use a lot of algebraic data types. From time to time, I also speak at Scala Taiwan meetup. And I also have some beautiful stickers for whoever wants. Before we start talking about algebraic data types, let's define what is actually an algebra. It is a part of mathematics that studies symbols and operations that manipulate the symbols. Symbols and operations, that's the important part. Algebraic data type can then be defined as a type that is formed by combining other types. You take two types, you combine them somehow, and the result is called algebraic data type. We have two ways of combining types. One is called product, and the other coproduct. The product is formed from two types A and B by providing both the types at the same time. So product needs both types. Coproduct, which is also called sum, needs one of the types A or B. Maybe it's not clear now, but it will be clearer later. In Scala, we can create product by using a tuple. Tuple is a product by itself. So here we create a product P, which combines two types A and B. Another possibility in Scala is a case class. Case class itself is a product. The difference between tuple and case class is that case class is a name, and also it names the fields inside the case class itself. As you can see, in order to have a product, no matter how I create it, I need to provide both types A and B. I cannot have P without B. Coproduct, on the other hand, can be created by using built-in type either or using a sealed trait. Here, remember, coproduct means either A or B. So when I create a type C using either, that by itself can only have one A or B. Sealed trait, on the other hand, I can wrap the A or B inside these case classes under which extend the sealed trait. This is something you probably very well know. I can also combine or mix the products and coproducts. So here I can see a coproduct of products. And I can mix them as much as I want. I can take million of them, million of those, and I can combine them, and it will be beautiful algebraic data type. So with that, I can redefine, or I can add one more definition to algebraic data type as a recursive coproduct of products. This shows some naming. The C, the name of the sealed trait, is the type of algebraic data type. Coproduct has multiple variants. So each case class is one variant of a coproduct. Each variant has its own constructor. So in order to construct a value of type C, with this variant, I will use C1 constructor. These variants are both products, and each product has multiple fields. That's just naming. Now you can see, using the constructor, how to create a value. But very often we also need to extract the value from inside the algebraic data type. You very well know pattern matching. This pattern matching serves to extract the fields or values from inside algebraic data type. Having the same sealed trait as before, how can we implement this very simple method which converts a value of type C into a string? Well, by simply pattern matching. I'm pretty sure everybody already knows that. We can also write a pattern matching in a different form, here in form of function, where we can drop the keyword match. These two are pretty much equivalent. The beautiful thing about pattern matching is that the compiler can tell us if we forget to cover one of the variants. Here I forgot to cover variant C2, but the compiler will tell me, hey, you forgot the C2, go back and implement it. Unfortunately, this only triggers a warning. I think it should be an error, but it is not. Which means that your program will still compile. But at least the compiler will tell you that you forgot something. Let's see a few examples of algebraic data types. Yeah, I believe you are familiar with them. Option is one. We have a type option and two variants, some and none. This is widely used in Scala every day. Either is another example of algebraic data type. The type either actually expresses a coproduct by itself. So you can see that one variant wraps the first type and this other variant the second type. This is just another realization of coproduct. List or tree are another examples of algebraic data types. You can notice that here one of the variants contains itself or the type of the ADT. So we can nest them inside each other. One area where algebraic data types shine is modeling your business domain. And I believe that this is really the best use case of algebraic data types. Algebraic data types, they are holders of data. That's the only thing they can do, hold data. And you can use them to move data from one place to another. You can use them to manipulate data, to transform between different representations. You can also use ADT to express invariants. Invariant is a condition on data that you can rely on, that is always true during execution of the program. It will be more clear with an example. As an example, let's try to create a model of a customer. We have three requirements. One requirement, the customer has a name. Another requirement is that each customer must have at least one contact. And we also say what is a contact. It's either email, address, or phone. So the invariant is, for example, that each customer has at least one contact. This is something you can rely on during the whole program. Let's start with the contact. It's very simple coproduct with three variants, email, address, phone, something everybody knows. Now, we need to express somehow that the customer has at least one contact. We can do it in this way, where we add a field primary contact, which is of type contact, that must always be provided. And in case the customer gives us more contacts, we can also add additional list that can be empty. So if the list is empty, we have at least this one contact. There is a better way how to express this. We can actually combine the contact and list of contact into another algebraic data type. Let's call it non-empty list. So we created a new algebraic data type that represents a list that has always at least one element. And now putting it back to our customer representation, we expressed our invariant, the invariant that the customer must have at least one contact as part of the ADT. This has a very great consequence. You cannot create a customer or a value of type customer without contact. It's not possible. So the algebraic data type can actually help us to make our program more type safe. And one thing I consider extremely important, it makes illegal state unrepresentable. We cannot create a value with illegal content. For example, a customer without content. contact. We can't. That means whenever we have a customer in our program, we know that there is at least one contact. Let's show some advantages of algebraic data types in Scala. They can provide very accurate model, as we can see with the contacts and customers. You can go really, really deep with this. And actually, theoretically, you can represent any kind of model with any kind of invariance as algebraic data type. Sometimes it's very impractical, but it's always possible. It's kind of self-documenting. When you see this in the code, you don't really need to write much documentation about what can a contact be. You see it immediately. The compiler gives you hints when you forget something. We've already seen that. You cannot create a value with illegal or incomplete content. It's also a brilliant thing. And it allows us to use something called an Emic domain model. An Emic domain model is such a domain model without any logic attached to it. The logic is completely separated from the data. This is something that is strongly encouraged in functional programming, and it's an exact opposite from OOP. If you read some object-oriented programming guidelines, they tell you put them together. They hate Emic domain models. We love them. Thanks to that, we cannot have a mutable state in our domain, which means that all our objects are immutable. You probably know all the advantages. You can more easily parallelize or scale. It's easier to convert between different formats. If you have an Emic domain model, which means just an object without any logic, you can easily convert it to JSON and back. You don't need to care about any other special conditions or validations. It helps us to modularize. We can put our logic and data somewhere else, and we can reuse them more deeply. And I also believe that they help us to test in a more simpler way. Unfortunately, there are also some drawbacks in Scala. One is that the variants are also types by themselves. Can you guess what is the type of this list? It's list of sum of int. It's quite weird. But it's even weirder in this second case. Can you guess what is the type of the list? List of what? No, it's list of none.type. None is an object, and type of the object is none.type. Super weird. We would laugh if the list is of type option, list of option of int, right? But unfortunately, in Scala, it is not. We can bypass it by using smart constructors or by explicitly providing the type. But the type inference will work like this. It's pain to write it. This is a very simple algebraic data type, but you need to write, I don't know, 500,000 of characters just to express what is an option. Compare it with Haskell. It cannot be more short or more concise. Luckily, in Scala 3, it will be better. So this is what Scala 3 will use for defining algebraic data types. And as a bonus, in Scala 3, this constructor sum will create a value of type option. That means that in Scala 3, this list will be inferred as having type list of option of int. It's brilliant. The type sum still exists, but this constructor will not return a value of type sum, but value of type option. I believe you mostly knew all this. There is one maybe surprising connection between what you just saw and the world of mathematics. Before I start, let's remind ourselves, what is type nothing and unit? It's quite two weird types that exist in Scala. Type nothing is such type that has no value. You cannot create a value of type nothing. Then there is a type unit that has exactly one value. The value is written like this, empty parenthesis, and it's called unit. Just remember, nothing, no no value, unit, one value. Now I have a product, very simple product, a tuple of 4 booleans. Can you guess how many possible values this product can have? It's 16. We call them inhabitants. So inhabitant is a possible value of a type. How many inhabitants does the type B have? 8. How about this one? How about the type E? It has 1 inhabitant. Exactly. Let's go a little bit further. Now we have a product with 1 boolean and 1 unit. How many inhabitants does this product have?
2.
It has exactly 2. I can name them. True and unit and false and unit. It's all possible values of this type. How about the type B? It's also 2. And type C also 2. So we can see that if we put a type unit inside a product, it doesn't have effect on the total number of inhabitants. So to calculate the total number of inhabitants of a product, we take number of inhabitants of the types inside a product and we multiply them. So you see some intuition, like somehow it's very similar to multiplication of numbers. Now let's see if there is something interesting with coproducts. We have a coproduct with 3 variants. How many inhabitants do you think type T have? It's exactly 6. I can list all of them. I can create only one of these 6 values, no more. Now, we saw that in product there is a type that doesn't have effect on the number of inhabitants. Could there be something similar in a coproduct? It turns out that there is a nothing which doesn't have impact on the number of inhabitants. So type T here has 4 inhabitants. That's because I cannot create, I cannot use the constructor C. I can never provide a value of type nothing. So this type T can only have these 4 values. So in some way, the coproduct somehow corresponds to addition. You see the similarities, right? Now, what will happen if I put nothing inside a product? How many values type T can have? It's exactly 0. That's because I can never provide a value of type nothing. So 2 times 2 times 0 is 0. So the fact that you can see this vague connection between numbers and algebraic data types, it's not a coincidence. Algebraic data types, they form so-called semi-ring. It's hankan in Japanese. Semi-ring is a set that has 2 binary operations, addition and multiplication, and a set of laws. It's a very well-known laws like commutativity of addition, neutral element 0, neutral element 1 with multiplication, distributivity of multiplication, and multiplication by 0, which gives us 0. So the natural numbers and algebraic data types, they both form semi-ring. So they both have the same properties. That's why we can see this analogy between natural numbers and algebraic data types. And the analogy goes really far. You can actually go from one word to another, do your transformation with the numbers, or in this case, symbols, and then go back to the type. These 2 lines, these eithers, they are equivalent. They express the same thing. Maybe they are not represented the same in the memory, but they express the same fact. And as you can see, all the rules you know from numbers, they work exactly the same with the types. You can convert between them, and you can do the operations on any of them and then convert back. And for me, this is kind of a hint that behind algebraic data types, there is this very strong world of mathematics that gives me strong guarantees that my algebraic data types actually do and express what I think they do. And I believe that that will be all I wanted to say. I thank you for attention, and please, what are your questions? Well, no, then thank you again.